nothing. Hey, advanced topics. So we're just gonna, this is my first video. There's gonna be a lot of errors. We're just going for it. See what happens. So this is 1-1, it's a vector. So if you guys are in pre-calc, you know a vector is a direction and a magnitude. Okay, so there's an asterisk to that. If it's a position vector, it has position. But otherwise it does not. So this just means, oh great, I just cleaned my board, it's fading up here. This means that unless it's a position vector, it could be anywhere. So this vector, and this is the tail, and that's the head. Oh man, I should clean my board. It's fading on me. Sorry guys. So tail, head, and it's a direction and a magnitude. That magnitude, the length is the magnitude. Sorry, it's fading out. Listen, this being learned. So, so that means that this vector, if I were to copy its direction and magnitude over here, if I call this vector V, we sort of put that harpoon on it, and I call this vector W, I could say, because they're the same direction and magnitude, I could say that V is congruent to W. Oh my gosh. Anyway, so there's sort of two ways how we work with this. There's a couple things you need to know here. There's standard position. So, you know, this is sort of thinking of our normal axis, sich, where we measure from due east counterclockwise. So this is a vector. This would be the angle by which we measure it, theta. So this is what we would call standard position. And that cleaner. Let's not get it. No, we'll see. So, and then there's also, it's like an automatic erasing board, there's bearing, like a compass. So when you'll run into that more often when you were dealing with direction like north, south, east, west, right? And so bearing, since our compass needles point north, bearing goes north and rotates clockwise. So this bearing, so say that's the same vector, the bearing here would be very different. I'll call it phi just to keep it a separate symbol. So let's say this is, let's say here theta is 150 degrees. Usually in vectors we use degrees instead of radians, which is kind of nice. It's just radians, isn't that right? But that means over here, for phi, which is a bearing, I didn't write that down, that means that this one, okay, so this angle is the same, so this one right here is theta, so we know that's 150, we'd have to subtract 90 from it, so that gives us 60 degrees here, and so, and then, let's see here, so we'd say 90, 90, 90, so that's, let's see, that's 30, this is 30 degrees, that's a reference angle, 30 degrees, sorry. Now my light's going twitchy on me, that's great. So 90, 180, 270 plus 30 should be 300 degrees. I did the arithmetic right. So, little quick intro here. Let's see, I'm just going to put a little asterisk down here. Little asterisks. Position vectors. So you're going to hear me talk about this a lot. I need to attach my board a little better too. Position vectors have a tail, or I should say have their tail at the origin, and the head is the position. So So if a vector starts at 0, 0, and the head goes here, that point is one and the same. I guess I haven't gotten to vector labeling yet, so anyway, we'll get there. I'll come back to that actually. Like I said, I'm just going for it here, so I'm going to make some errors this first time. I'm not really good at editing yet, or have the patience for it. We'll see. So, okay, so let's say we have a vector v. And let's say it has components 3, 4. Now, how I've always thought about this is vectors are direction and magnitude, but I think of a vector as also meaning change. So when I think of this vector, I think this is the change in x, and this is the change in y. So vector 3, 4, if I were to draw it starting from the origin, I would go over 3 right, 1, 2, 3, 4 up. And so from 0, 0 to this point here, this vector would be 3, 4. However, it doesn't have to be there. I could start it here and go 1, 2, 3 over and 4 up, approximately. And that vector will be the samesies, right? So it doesn't care where it is unless it's a position vector. Position doesn't matter unless it's a position vector. Now there's some other ways to label these. Sometimes some people like this. I've never been a big fan. Some people, like at the U when I did vectors, it was always written like this. And then, although this book doesn't get to this notation until later, you would not be silly if you remember doing things like this. This is another notation, but we're coming to that. This, I think, to really understand that, you have to do a little bit more vector scaling, multiplication, and addition. So we'll come back to that one. Let's see here. The magnitude of a vector. Let's see. I wish my whiteboard was a little bit bigger. So let's say, so the magnitude of a vector, I think I can squeeze it in here. So magnitude of a vector, that light, I'm going to turn it off. Okay, hopefully it's not too dark. The magnitude of a vector, which is denoted like this, it's got these absolute value bars around it. In fact, absolute value, magnitude, oftentimes interchangeable, not always, but. And so the magnitude of this vector, for example, can be found just by using the Pythagorean theorem. So in this case, oops, that's not what I want. 3 squared plus 4 squared. Well, that's 9 plus 16, that's 25. Square root of 25 is 5. So, we're using our friendly right triangle trigonometry, right? So if we think about this as being a triangle, this change, this is our change in x, this is our change in y. So anywhere these are, we can sort of impose components onto them, the horizontal component and the vertical component. So there's that. So let's see here. Let me just summarize a bit here. Let me erase this, and maybe I can maybe after erasing it, it won't fade on me so much. I don't know, I'm trying this out. I think this is easier for me to use this instead of a virtual whiteboard, but I just think it'd be really slow and cumbersome, but we'll see. So, let's see. So, just to summarize, a vector v, how I think about it is it's sort of a change in x and a change in y, or, what's more often written is, gosh, it just doesn't, is you might say it has components v1, v2 is what they'll often say in the book, but how I think about it. And so then that means that our magnitude of that vector can be found by squaring the components and summing them and square rooting it. So, okay, so there's that. That's really annoying. Okay, let's see. For non-right triangles, now this is, I think this is a little bit important here. I'm just going to say this piece here. Just a little bit to remind yourself about non-right triangles, because they do come up in vectors. Or sometimes, I should say, sometimes it's not easy to impose a right triangle onto a situation. It's easier to use a non-right triangle. And so, just for non-right triangles, okay, trying to remember the name right now. It's been a long summer. I can't think. If this were a real classroom, someone would shout it out. So for non-right triangles, I'll just have you remember there's a law of sines. Really quickly, because my ink fades for some reason. Law of sines, and there's sort of two ways to write that. So if you have a triangle, let's see here, let me just put it over here. So that's sort of the convention is the sides are lowercase, and then the opposite angles are uppercase, right? So for this triangle, we know that A is to the sine of angle A, as side B is to the sine of side B. And these shouldn't be uppercase, whatever reason, I just do that. Side C is to the sine of angle C. So, hope I said that right. And of course, the reciprocal is the same as well. It can be shown pretty easily that this is true, right? And which one do you choose? Well, I usually choose the one where I'm solving for is in the numerator. Because solving for the numerator is easier to me. So, and of course there's a lot of cosines as well. We won't do a proof right now. We'll prove these in pre-calculus. So there's kind of like two of them. This one's for sides. So that's side c squared is equal to a squared plus b squared minus 2ab cosine. And I'm going to put this to be specific, angle c. So these are sides, and that's an angle. And if you solve for this, you can also get this one. It's pretty easy to find out. So there's angle c, and that's equal to, okay, over 2ab. That's a product down there. So don't forget about that. This book likes to throw that in a little bit when you're starting vectors, because we're going to be creating some triangles and different things and whatnot. So let's see, what else should I say here? Okay. Well, you guys can pause it. I can keep going. If you need to pause it, I don't need to pause for you guys right now because you're watching on an electronic device, which means it's fine. You can pause it and do whatever. Isn't that great? I'm going to have to, I'm nervous about this thing falling off the wall. Okay. Okay, so let me just say, let's say this. I just want to talk about this a little bit. So let's say we have a vector in standard position. Let's say the vector is like so. Right? One thing I want to be sure to mention is that negative v is literally just the opposite direction and same length. Right? And so, say this vector v, I won't do the labels, but say this vector v, no, I'll blue this time. Say it has components 3, -5, okay? And so, negative v, we're kind of getting into, is going to have the opposite signs, right? So, it's -3, +5. And that sort of leads us right into scalar multiplication for vectors, which I don't think, let me just see here when I'm supposed to talk about that. I'm not supposed to talk about that till 1-3? That seems silly. I want to mention it. So, so say we have this vector b, this 3, 5. Scalar multiplication for vectors is such that if you have 2 times v, now this is a scalar, which is just a number, times vector v, that's literally going to be 2 times 3, negative 5. Okay? The blue seems to be better. And so that would be 6, negative 10. That would be that vector. Now, what you would see if I were to graph this is that it's literally twice the length. So this is twice the length of v. Okay? So, in fact, if we were to calculate this magnitude of v, if you don't believe me, this board's going to fall. And then it's 9, 3 squared is 9, negative 5 squared is 25. Let's see, so 25 plus 9, that's 34, right? Okay, and then, maybe this isn't the best example, this one was off the cuff. And then if I want to do the magnitude of 2v, that would be 36 plus 100, that's 6 squared, it's 10 squared, so that's the square root of 136. Well, let's see here. Let's see if that's a multiple of 4. Does 4 go into that? Let's see, 4, does that go into 136? It should. So that goes in there 3 times, and then that's 12, 116, so that's 4 times, so that's the same as 2 times the square root of 34. Why was I looking for 4? Well, because under the radical, square root of 4 is 2, that would make it double. Okay? So, scalar multiplication, it also works for fractions. You can scale it down to half sizes, quarter sizes, fifth sizes, whatever you want. In fact, if a vector is 1 unit in length to begin with, you can multiply by any number you want, and that's how long it's going to be. That's powerful. Okay, I'm going to pause here. 1, 2 is on planes, so we kind of jump around and talk to planes here for a little bit. They are certainly related, but I'm going to pause there. So.